Very warm welcome from my side to each one of you out there. Let me remind you where we had stopped in our very last lecture. We were dealing with certain results about the operations on sets. We were not just dealing with them, in fact we played with them in every possible sense. We allowed one operation to go inside the parenthesis and distribute over the other operation. We allowed that the swapping of the latter and the former sets between the intersection or the union operation is kept. What not did we allow? And everything was allowed and covered by the very 6 laws that we encountered in the last lecture. And in the last lecture, we also discussed some alternative proofs of the same things which we had done before. Why did I tell you that? Because that should be a smart approach towards solving a particular result. The moment you start visualizing mathematics, it becomes cakewalk for anybody. And that is what you have to master. At the end of the day, why did John Venn give such a big contribution of Venn diagrams to us? Only to get rid of the problem of not being able to visualize mathematics. And then only can you combat your fear with mathematics. Once we were dealt with the 6 results about the operations on sets, we are now geared up and all set to start our very 7th result. The 7th result I promised you that I would be presenting in this session. Let's see what the 7th result says. It says, suppose I have 3 sets A, B and C and I have taken the difference of the 2 sets B and C. What do you think comes if I take the intersection of A with the difference of B and C? Well, in that case, you are definitely going to land up to a set, but how does that set looks like? If you all remember, we have already dealt with this result, but in a long and elaborative format. This is a much smarter technique to tackle with this. What do you think turns out? Well, the same thing happens. The intersection sign goes and travels inside the parenthesis, acts with B. It again goes, acts with C without affecting the minus sign sitting inside. And therefore, we obtain this to be equal to A intersection B minus A intersection C. Now is the time to actually digest that this is true, because mathematics says don't rely on your eyes. We need to bring the proof on, which is as follows. Suppose I start with the set sitting on the very left hand side. What is it? It is A intersection B minus C. Yesterday also I told you that A minus B has a different format, which is, if you have the difference of 2 sets, you can write this as A intersection B complement. And using this particular result, I don't know how many more results could we prove. This is so damn important. This is the same thing I am going to bring to use over here as well. Because I have a B minus C in picture, and therefore this expression becomes equal to B intersection C complement. Because it says keep the former set as it is and take the complement of the latter set by just including an intersection sign in between. That is what we have done with B and C. Now is the turn to do something tricky. What am I going to do is, I am going to, with the help of associative law, club A and B together and leave alone C complement. What is the associative law? Associative law said that if you have intersection of 3 sets, you can do this intersection in 2 ways. Either you can take the intersection of A and B first and then take the intersection with C, or what you can do is take the intersection of the latter two first and then intersect it with A. Both of these will result in the same set. This was what was the very associative law. That is what I am going to use here. And so I am going to bring B towards A and leave alone C complement. With the help of associative law, this is what I have. Once you have obtained this, what is it that I am going to do is use the identity law. What was that? Do you remember I had asked you which is that set with which if any set is taken union with results in the same set? You have to answer this query because I had already asked you. What do you think should come here such that what I obtain is again A? That means I want something here which does not change the identity of A and leaves A as it is. And we had concluded altogether by the very firm discussion that the empty set is going to do that work for us. And this is the fact that I would be using right now in the proof, because it's not just A union empty set is A. In fact, I can also come from the right hand side to the left hand side. Wherever I see A, I can replace that with A union empty set because they both are the same. This is what I am going to do here. Now A intersection B intersection C complement is one single set. If I take the union of empty set with A intersection B intersection C complement, these two statements are exactly the same with the help of the identity law. Is that understood? And therefore what I obtain next is the same thing. Now the thing is how to deal with the empty set. Again, this is the tricky part. For this, I am going to take you to the world of Venn diagrams, wherein we are going to play, shade, color and understand the concepts. What is the Venn diagram? Here that I am going to draw is, suppose this is my universal set and I take two distinct sets A and B. Okay. Now I am saying, what do you think is the intersection of, suppose I say, compute this. That means you have to find the intersection of A intersection B with A complement. In order to find this intersection, I have to shade two portions in the Venn diagram. One is shade A intersection B section and then shade A complement section. Then the task is to find the common shading portion among the two. Okay, that is going to give us the members which are sitting inside A intersection B also and A complement also, and that is the set which we want. Let us try and shade A intersection B, which is the set of all those members sitting in A also and sitting in B also. And that, my friends, you already know is denoted by the overlapping portion in the Venn diagram, which is this. This particular blue shaded portion is my A intersection B. Once A intersection B has been obtained, now is the turn to shade A complement. Let's see what A complement is. So A complement says just leave A and shade everything else. We just have to ignore A. Ignoring A, if I try and shade, I basically get I have to ignore A, therefore I cannot pass my lines through the set A. These white vertical lines basically stand for A complement. Can you see any region in the Venn diagram where both blue and white lines come together? Either a region has white lines or it has blue lines. There is no region which has both white and blue lines together, which means there is absolutely nothing common between A intersection B and A complement. And sets which have nothing are known as empty sets. We also have a symbol for them, which is the symbol phi. This particular concept is what I am going to use in order to prove the very claim at which I was. Which is, we were stuck here. We had just written this set to be equal to phi union the same set with the help of the identity law. And now is the turn to again replace phi with what? With A intersection B intersection A complement. Because phi is equal to this set itself. Let's do that. And replace phi by A intersection B intersection A complement. This is just the replacement of phi. Once phi has been replaced, copy down the stuff which is supposed to not be disturbed. And that is union A intersection B intersection C complement. Observe carefully what is it. A intersection B intersection A complement. A intersection B intersection C complement with a union in between. Let me remind you of something, which was, if I have A intersection B union C, it opened up as A intersection B union A intersection C. This was the very distributive law which we are already aware about. If you observe the right hand side, what is happening is, the first set in both the expressions is same. The second set is changing from B to C. The operation inside the bracket is the same intersection and the operation outside is union. Let's see what is there with us. The set sitting with the primary, the very former set, is A intersection B in the first bracket, A intersection B in the second bracket. What is changing is the A complement and C complement sets with intersection sign within the bracket separated by a union sign. Exactly the same scenario. What happens this set to be equal to is, the very first set comes outside with the intersection sign and the sets which were changing come together with the union sign. And so the set which is coming at first in both the brackets comes out alone with the intersection sign, and this expression turns out to be equal to this. The next portion, let's go back, is that I am supposed to collect the members which are changing, that is B and C, club them together with the help of a union sign. Here the role of the changing sets is being played by A complement and C complement. So we have to club both of them together with the help of the union sign. Let's go back and do that. So we have A complement and C complement together clubbed with the help of the union sign. This is just an inspiration from the distributive law. Now next what we have with us is A intersection B is left unchanged. You all know which law is going to be applied over here. I am sure you remember because this we are using extensively now. You know that A union B complement was A complement, B complement separated by the operation opposite to the operation already present. Union is present, separate by intersection. If intersection would have been present, write the same two sets again, separate by union. This is what you have to do. These are your very De Morgan's laws. This is what I am going to bring into light right now. You already have A complement union C complement. Can you see anything like that among here? The expression A complement union B complement is what matches to what we already have. And if you have something like a sets complement union another sets complement, it is equal to take the intersection of both sets and take the whole complement. Which means you just have to take the union of both sets and take the entire complement. This is what is the application of the De Morgan's law. What is the next step? Now again let me take you back to the very first law, which was A minus B equal to A intersection B complement. This I have marked a star over here because again it has come into use. Just observe what is happening. If you have something like one set being intersected with the complement of another set, this is equal to the difference of both sets. The picture that we have is that the set A intersection B is being intersected with another set's complement. This is a similar picture like the law that I showed you right now. And therefore, this becomes equal to the difference of the same two sets, which means A intersection B minus A union C. Is that understood? This is what it is. First set minus the second set. Have I done something wrong? Can anybody point out? The De Morgan laws here said that if you have union sign between the two sets complements, it gets converted to intersection. I really over here had A complement union C complement, and that had to get converted to A intersection C whole complement. I hope you guys must have caught that and corrected that in your notebooks already. And therefore, I do that formality too. This is A intersection C whole complement. Again, nothing changes by the usage of that law. I still have the picture that one set is intersected with the other set's complement, which means I just have to take the difference of both sets. This difference turns out to be the difference between A intersection B and A intersection C. This is what is the very thing that we wanted also coming to be on the right hand side of the result. A intersection B minus A intersection C, and that is what we have obtained by all this explanation. Once this result is thorough with you, I can assure you the very memory of these 7 laws is going to help you a lot while dealing with the questions. So note this down without any mistake and be ready for the next section. So guys, we are done with the 7 laws about operations of sets. I hope that was a fun journey in order to unfold how many ways can a set look like or be interpreted as. We now go on to the very next new and the last topic related to sets. And so I bring before you the very last topic of set theory, which is number of elements in a set. Let me quickly tell you some small introduction. We have till now dealt with the relationships between sets in many forms. That relationship was actually established by the very way in which members of these sets interacted with one another. And therefore, the entire relationship between sets got dissolved to the interaction between the members. And therefore, right from the beginning, we are stressing on the members which are sitting inside the sets and how are they behaving. More than that, while studying finite sets, I made you introduced by a concept known as cardinality of set, which was actually the number of elements sitting inside a set, in fact, a finite set. But what if you don't have a finite set? In that case, maybe you won't be able to count the number of elements on your fingers and conclude that these many members are sitting in the set. For that, the Venn diagrams approach comes into picture and an arbitrary case of a set having any number of members comes into play. This concept basically helps us to evaluate number of members sitting inside any set, mind it. And we are going to do that with all possible sets. Suppose I have a set A in picture. Take any set A, okay? Then number of elements or members in A is given by this symbol, which is small n with inside the bracket that set sitting whose members we are interested to count, and it is read as number of elements inside the set A. Once this notation is clear, we are in a position to find out the number of members sitting inside all possible sets. The very first result that we have on number of elements is to find the members, how many members are sitting inside the set, which was the very first set obtained when two distinct sets were given to us. Suppose I am given two sets A and B, the new set that I can form with the help of very first operation valid between two sets was the union of two sets. And that is what, my friends, is the very first formula. It says number of members in the set A union B is equal to number of members in the set A plus number of members in the set B minus number of members in the set A intersection B. How are we going to memorize this formula? For that, we need to see what's going on. And for seeing, we already know the tool that we have with us, which is nothing but the Venn diagrams. So suppose I am taking my distinct sets A and B, and now I am interested in how many members are sitting inside A union B, which means the whole of A and the whole of B is included in A union B. The formula says, and it is obvious also, if you have to find the total members in A union B, you will have to take all the members of A and have to take all the members of B, because that is what you need inside the set. And therefore, all the members of A means you will collect all the members sitting here.